What is up, you guys? Welcome to another lecture on optimization algorithms, where the goal is very clear. Given a function f of x, find a point x that minimizes f of x. In this one, I will show you what damped Newton method is and how to use it with the exact line search method. We will approach both methods from intuitive and animated perspectives, and we'll show you how to use them together. But not just that, I will also show you how to implement and animate those algorithms on Python. The following video was recorded on NVIDIA's Jetson Orin supercomputer in Abu Dhabi, the UAE, and under a Creative Commons license. I'm Ahmad Bazzi signing in on this one. First, let's talk about damped Newton's method and why it works. So given an initializer x0, we pick a direction dk satisfying the following linear equation. Like Newton's method, we use curvature information, that is, information relying on the Hessian so as to take a directed route. Let me show you why we are using dk direction towards the negative of the gradient. Damped Newton, just like Newton's method, makes a local quadratic approximation of the function based on information from the current point, and then jumps to the minimum of that approximation. Just imagine fitting a little quadratic surface in higher dimensions to your surface at the current point, and then going to the minimum of the approximation to find the next point. Finding the direction towards the minimum of the quadratic approximation is what you are doing. As a matter of fact, this animation shows you why, in certain cases, Newton's method can converge to a saddle or a maximum. This all depends on the eigenvalues of the Hessian. If the eigenvalues of the Hessian are non-positive or even a combination of positive and negative eigenvalues, in those cases, the local quadratic approximation is an upside-down paraboloid. The damped Newton method damps the derivative by a damping factor sk, where sk is between 0 and 1. Otherwise, it's not damping anymore, it's amplifying. Usually, this sk is obtained by a line search, like exact line search, Armio, backtracking, Wolf criterion, and many more. Finally, we walk in the damped direction. Note that if sk equal to 1, then we are doing a classical Newton step, right? And we stop according to a stopping criterion, like maximum number of iterations, proximity of xk plus 1 relative to xk, or how small the gradient at sk plus 1 gets. Next, let's talk about the line search we are going to use in this lecture, which is the exact line search. For the exact line search, and as the name suggests, we want to find the best alpha that exactly solves the update equation, given x and p. Here, x is the point we are standing at right now. So at iteration k, this is xk. And p is the direction we want to take. The alpha tells us how far we go in direction p. So if alpha is 0, we stay where we are currently at. And if alpha is 1, we take a step of p, and so on. To solve this exactly, we derive the first order conditions by setting the derivative with respect to alpha to 0. Rearranging a bit, we finally get the equation p transpose f prime, or the gradient of f, at x plus alpha p is equal to 0, which is the exact line search condition. Perfect! Now, let's implement what we have demonstrated on Python. First, let's import some packages that we will be using along the way, like numpy and sympy. Then we define an independent function for our line search. For that, we declare a function called exact line search method, which basically takes in the function, the current x value, the alpha to test, and the direction p. And if the exact line search condition is satisfied, we return true, else we return false. Then we implement our damp Newton method. Our function will take in the function f of x, gradient, Hessian, and an initializer x0. We define the maximum number of iterations to be 500. Let's also define our raw to be something less than 1, say 0.55. The sigma as well, fix it to 0.4 and initialize our k to be 0. K will be the number of iterations. Set a very small epsilon to define when to stop taking steps. We will see how in a bit. So this while loop defines the maximum number of iterations, and within I will compute the current gradient and Hessian. Next, I will solve the equation hk dk is equal to minus gk to find the direction to take. Next, if the direction to take is very small in L2 norm, then it is not worth to continue iterating or walking, as the step size to take becomes less than 10 to the power minus 5 in the L2 norm sense. Let's define m and mk to be 0. Then do a line search. We keep shrinking our row by multiplying it with itself or doing row power m for the mth iteration of the line search until the line search condition is satisfied. Then we break. And update our x0 to the next value, where we step an amount of row power m times the direction dk. We increment k to say that we are going to the next iteration. So that's it for the main loop, and what comes after is really just some printing to show the value we have converged to and to print the value of the function at the converged point, as well as the number of iterations that we took. First, let us define counter variables for the number of times we called our function, gradient, and Hessian. It is important to benchmark the number of computations done for any given algorithm. I won't display them here, but it's good if you want to run some computational analysis. Next, let's define our variable through SymPy's index-based method. Followed by the function f x0, x1. It is clear that this function is minimized at x0 equal to x1 equal to 1. Then we compute our gradient and Hessian expressions with the help of SymPy's diff function, which simply performs a derivative. Next, let's generate the function, gradient, and Hessian's Python numerical calculation function using NumPy and with the help of SymPy's lambdaphi function. Then we define the functions as function handles, where fun represents f of x. This is only done to count the number of times we call f of x. For the same reason, I will create a function handle for the gradient and the Hessian. Last but definitely not least, I will call my function to test how it performs for different initializations. First, let's create a folder called Animate Iterations. And within this folder, a script called func.py, which contains all my Python animation functions. I will start by importing NumPy. I will create two methods for animating in 2D and 3D. I will start by animate 3D, where I will plot f of x on a 3D axis and show the point xk per iteration in 3D. I will also mark the path taken. The inputs to animate 3D are the function f of x, the axis extreme values of x0 and x1 axis, as well as the x0, x1, and f of x values taken per iteration. I will import some modules in this function like pyplot from matplotlib Axis 3D from MPL_toolkits, and animation from Matplotlib. Let's create a mesh grid based on the extreme values inputted. The mesh grid will contain 100 by 100 points. Then we evaluate per xy value the z value, which is fx0, x1, and then reshape accordingly. Then initialize a 7 by 7 figure and instantiate a 3D axis using axis 3D. Then let's plot z versus xy using the following design parameters. Set the x-axis as x0, the y as x1, and the z as fx0, x1. If you're wondering why I have the dollar signs surrounded by the variables, it's because I want to render the symbols as LaTeX expressions. Next, let's rotate the 3D plot to the following view angle. Next, we create the animation where the path then is colored in purple. And the point representing xk is animated as a purple star. Next, we use the following parameters for font sizes of our text. Then we define a callback function, init_2, to initialize our animations where the line and point properties are empty. The text is also set to empty. Following init underscore to, we have another callback function, which is animate underscore to, that takes the iteration number I as input and sets the current value of x0, x1, and f to plot the line and set the point. Optionally, you can have a legend. And before we wrap up this function, we need to generate our animation using animation.funcAnimation. We pass it the current figure and the callback functions animate underscore to and init underscore to. We also set the following parameters like number of frames, which is clearly the length of x0 underscore vals or x underscore vals, since each value represents a frame in our animation. Before closing the function, we show the plot. Then we go to animate 2D, where I will plot f of x on a contour plot and show the point xk per iteration in 2D. The inputs to animate 2D are the function f of x, the axis extreme values of x0 and x1 axis, as well as the x0 and x1 values taken per iteration. I will import some modules in this function like pyplot from matplotlib and animation from matplotlib. So axis 3D is not needed. Like we did with Animate 3D, let's create a mesh grid based on the extreme values inputted. The mesh grid will contain 100 by 100 points. Then we evaluate per xy value the z value, which is fx0, x1, and then reshape accordingly. Then initialize a 7 by 7 figure and plot the data we have using a contour plot. Next, we create the animation where the path then is colored in purple and the point representing xk is animated as a purple star. Next, we use the following parameters for font sizes of our text. Then we define a callback function init_1 to initialize our animations where the line and point properties are empty. The text is also set to empty. Following init_1, we have another callback function, which is animate_1, that takes the iteration number I as input and sets the current data of x0 and x1 to plot the line and set the point. We now add a legend, if you want. And before we wrap up this function, we need to generate our animation using animation.funcAnimation. We pass it the current figure and the callback functions animate_1 and init_1. We also set the following parameters like number of frames, which is clearly the length of x0_vals or x_vals, since each value represents a frame in our animation. Before closing the function, we show the plot. Now, after we're done with our Animate Iterations module, we import it as follows. We start by storing variables for x0, x1, and f of x0, x1. The example I am about to show you is on a 2D function. Hence, we have only two variables, x0 and x1. So I will store all my variables in x0 val and x1 val, and the evaluated function in f val, which is basically f evaluated at x0 and x1. I will then append the current value I have where the first value of x0 is stored in x0 vals and the second value of x0 is stored in x1 vals and the function in f vals. I will now append the current values of x0, x1 and f of x0, x1 at iteration k. Finally, we will return all the stored values. We start testing with Animate 2D and 4 different initializers. The convergence is super fast, so you see how fast this animation is. This is of course opposed to methods I'm about to show you in future lectures we are about to explain, like using damp Newton combined with Armio or the Wolf line search and other quasi-Newton type methods like symmetric rank 1 algorithm and the Broyden-Fletcher-Goldfarb-Shannel algorithm, where they approximate the inverse of the Hessian. Thus, this convergence will not be as fast. And that's about it. If you enjoyed the video or found anything useful, you can support me by liking my video and subscribing to my channel. If you have questions, kindly leave them down in the comment section below and I'll get to them as soon as possible. I am very grateful for all the support I received over the years, so thank you so much. I'll see you then.